Hey everyone, welcome to the Homework 2 walkthrough for Bioengineering 335. We're just going to go ahead and get started with question 1. And it's saying that we have a cylindrical limb. So we already know that we're in cylindrical coordinates. And then we have a cylinder of bone 4 centimeters in diameter, right? Surrounded by a 3 centimeter thick layer of muscular tissue. Great, and right off the bat, the first thing I'm going to do before continuing on with the question is I'm going to draw a diagram. I have right here, as you can see, I'm just going to make it really big. And we have, sorry again, excuse my drawing. But we have our limb, and then I'm going to go ahead and draw the core right over here. And with our core, great. We have it in 4 centimeters in diameter. That means we have a 2 centimeter radius. So what I'm actually going to do is I'm going to say this is 0 centimeters, right? And then I'm going to actually denote this as our bone, B for bone, is 2 centimeters. And then we have right over here our, what is this? Muscular tissue. So we're going to say RM for muscle is what? We have thickness of 3 centimeters. So that's 5 centimeters. So that's how we first have our initial drawing. And we are assuming that the blood or the bone generates no heat. So no heat generation, right? And then we have the muscle layer generating heat at a rate of 3,000 watts per meters cubed. So that means our Q met, right, is 3,000 watts per meters cubed. Okay. And then we have the outer surface of the 3 centimeter muscle tissue layer at 30 degrees Celsius. So right here, we know this is 30 degrees Celsius. Okay. So these are the things we know. Great, and we are asked to use thermal conductivity values from the table on page 1243 of Brazilian-Diller. And if you don't have a copy of the textbook, please let us know, and we're more than happy to send you those values as well. Okay, so the first part of the question is asking us to set up and solve the boundary value problem. And it's asking us to include an appropriate figure. And then as a follow-up, it's asking us, what is the temperature of the bone? Well, setting up and solving the boundary value problem, as we talked about in quiz section, we're going to work through this through layers. And then we are looking for what? We're looking for the temperature profile, right? As we move along R. We did an example problem of this at the end of quiz section where we had 2 layers, right? We had 2 layers. One had Q met, and there was an insulated layer right on this side. And we were asked to draw the heat, the temperature profile. And this was in rectangular, right? So this question is essentially the same question, but what? But I guess you can think of it as going the other way. This way, we're looking at it this way. And also we're looking at it in cylindrical. So that's how this question differs a little bit from that problem that we did in quiz section, but it is inherently very similar. Okay, so don't be worried about this question. All we're doing is we're doing it in cylindrical coordinates, and it looks like we're just working the other way around because the first layer does not have QMet, which is also applicable for us, right? So that is essentially what we're going to be doing. So with these boundary value problems, right, our goal is to find the temperature profile. And what we can do is we can always work from one layer at a time, okay? We can find all the boundary conditions relevant to this specific layer, and then we can move forward, right? We can use our equation that we determined from class and quiz section, right? Right over here. right? We can use this for each layer. And if there's no Q met, we're going to cross it out and we're going to work with just these components, right? And that's essentially what we're going to do for each layer. So I'm going to walk us through the bone layer, and I would like you to try out the muscle layer, but we'll keep going and we'll get started, okay? So also I'm going to label this as the bone, and then this is the muscle, okay? Great. Now let's start with the bone first. With the bone first, right? We should always understand our boundary conditions of the bone and any of the layers. That includes the bone and muscle interface, right? That's part of the bone. So we need to look at our boundary conditions first, always, okay? And we're going to look at our very first boundary condition, which is what? We know dt dr equals 0 at r0. And that is by the symmetry condition. Symmetry. Sorry, I was struggling there for a second. So by symmetry, we also know this because there's no Q met in bone, right? We don't have anything that's generating heat, okay, in the bone. And by symmetry, we also know that dt over dr is 0, okay, at this point. That's really important to note. That means what? That means we have, as I wrote earlier, essentially like the Laplacian operator for temperature plus Q met equals 0, we essentially have 0, right? This is another way to think about it too. And that means if we actually work it out, we'll also see dt dr equals 0, okay? We're going to look at that. We're going to look at making sure that's right in another way as well, okay? Great. And that's specifically around the central axis, okay, at r equals 0, specifically. Second, we also know that at temperature, the temperature profile, right, at radius bone is going to be some temperature, and we're going to label that temperature bone, okay? We don't know that yet. We don't know it. Don't know. But it's important to know, right? Because that will allow us to solve for our next layer. We do need to know that this temperature exists, okay? Great. And then we're actually going to jump right in to what we were doing up here, right? We're going to bring that down. So we have, right, our Laplacian operator equals 0 for temperature, right? And when we write this out, as we derive this in quiz section, right, starting with the conservation of energy, right? It boils down to the conservation of energy, and we were able to simplify in this way, right? If we write it all the way back out as it is, we have 1 over r times the derivative with respect to r of r times the derivative of temperature with respect to r, right? Equals 0. Let's keep working this out. Well, what happens? We can, I'm actually going to add another page. I see the next question. Great. We can see when we move this to the other side, right? It's going to be canceled out, right? And we can also move the dr to the other side, right? So essentially, we just have the derivative of r times dt dr, right? If we had, for example, q met, right? And we move this to the other side, well, those wouldn't cancel out. They'd be multiplied with q met, right? So please keep that in mind. This is only because we don't have q met. So now that we have this, we can take the integral of both sides, right? Of course, integral of the derivative cancels out. And we're left with r dt dr times or equals what? Equals a constant, right? Because we just took the integral. And now we can do the exact same thing. We can move the dr to the other side, right? We can take the integral. We can also move the r to the other side. And what do we have? Well, the integral of a derivative of the temperature, again, is just the temperature, and that is the temperature profile, and that is what we are looking for, right? And we also have, looks like it's a constant, right? So constant remains. And we have 1 over r dr, which we know is natural log of r. And then what? We still have a constant. So looks like we have 2 constants we need to solve for. One is based on the derivative of temperature, dt dr, and another one is just the temperature, right? It's a value of the temperature. So we know from earlier, let's scroll up a bit. We know r times dt dr is equal to C1. We figured this out, right? So why don't we use that expression, right? We know r times dt dr is equal to C1, right? Well, what else do we know? We know by our boundary condition number 1, right? Boundary condition number 1 states that dt dr equals 0 at r equals 0 by symmetry, right? So that means we have 0, right? 0 times 0, 0 equals C1. So there we go. We already have our first constant. That means T of R is just C2. Well, that means that the temperature profile doesn't change. Is that right? Yes, that makes sense. When we talked about an insulating layer, right? We had the insulating layer, the temperature profile was the same, right? Throughout for the insulating layer. We talked about this. That's why, because we have dt dr, or x in our case in quiz section, is equal to 0, right? That's why we knew that the temperature doesn't change when we did the math too. That applies just as well here, okay? So try to understand why something is, okay? So we know the TR, right, is C2. That means, right, as we said, our boundary condition number 2, right? We're not going to leave it just a C2. We're going to use like our temperature kind of phrases that we used. The one that we used earlier was TRB is TB, temperature bone, at temperature at radius bone, right? And that means we have temperature bone is equal to C2, right? And therefore, temperature profile of the bone is just the temperature of the bone at RB, okay? So that means the temperature is constant throughout the bone, okay? Temperature at bone, T is constant. And not at TB, it's equal to TB, right? Great, and this is because of our insulating layer. Insulating layer or dTdr equals 0, right? That's what makes that happen, okay? So we just solved for our first layer. And the next thing we're going to do is we're exactly going to do the same thing, and we're going to just rinse and repeat, okay? This is nothing scary. This is nothing really new. We've done this before earlier in quiz section. We're just going to be repeating it again in cylindrical coordinates, okay? That's all we're doing here. So let's keep going. And it looks like I'm out of paper, so I'm gonna add one more, okay? So now we said bone first. Now we have muscle next. Muscle next, right? We're gonna do the muscle next. So what did we start with when we did the bone? We started with our boundary conditions, right? We started with our boundary conditions. We did our first two. So our third boundary condition is going to be something we all know, right? We know our K for our bone, right? Keep this in mind. This is pretty important, not muscle. The thermal conductivity of our bone times dt dr at r rb, right? At this interface. This is specifically at the interface. That's really important, right? Is equal to the muscle, thermal conductivity of the muscle times the change in temperature, right? Over per with respect to radius, change in radius is at our bone, okay? At this interface, right? This is really similar to what we did for our velocity boundary conditions when we were talking about fluid flow, right? We know this. This is known. We know this. We know this boundary condition, all right? Okay, our fourth boundary condition is really similar to our second boundary condition. We're going to say that the T of at Rm, right, at the end of our muscle layer is going to be an arbitrary temperature muscle, which we actually do know is 30 degrees Celsius, okay? We actually do know this. So the fifth boundary condition is going to be the heat flux out of muscle times the cross-sectional area is equal to the heat generation of muscle times volume. And why is this? Why? Well, the reason is because all of the heat generated, right, in our muscles are going to be flowing out, right, of that cross-sectional area. And why is this important? Why is this important, right? So we have heat generation generated flows out, right? Flows, right? Flows out. We know this. So that means we have our Q metabolism, right, times our volume is equal to our Q muscle times cross-sectional area, right? Essentially, we're setting our big Q's equal to each other, right? Big Q's. We're setting our big Q's equal to each other, okay? Let's see the math, right? So we have our Q metabolism times our volume, right? So we know our volume of this layer is going to be pi. We have, let me just draw it again really quickly to show you, right? We have, this is RB, this is RM. So that means we have RM squared minus RB squared times our length of our cylinder, right? I guess it's like our appendix or our limb. Sorry, that's the right word. Our limb, right? The length of our limb, which we aren't given. And we have it equal to our Q muscle. What is our Q muscle? Well, it's negative K muscle dt dr, right? At R muscle. Do we have it is equal to and then you multiply it to and then you multiply it by 2 pi rm L, right? This is our cross-sectional area of our flow. the 2 pi rm, right? Great. So in the end, let's do some canceling out. We cancel out the pi's. We cancel out, what else can we cancel out? We can cancel out the l's. That's it. Well, we can rearrange this to get dt dr at r equals rm is equal to what? Well, let's move. I see the negative. We can move the negative over. I'm going to use blue. Negative q met, right? Over what? Well, km. There's km. I'm using blue to denote what I'm using, times. Let's put the rm minus rb squared on each over 2 rm. Great. So this is yet another boundary condition, right? This is a boundary condition of dtdr at rm, okay? Let's keep this in mind. This is a boundary condition, okay? We just derived the boundary condition of dtdr at the end of the muscle at rm, radius rm. And we can use this later, and I'll show you some options on what you can do for this problem, okay? So now what? We just spent a lot of time looking at our boundary conditions, right? Do your usual analysis. That's it, right? You do your usual analysis. There's nothing really new or scary about this, right? We're going to start with, right, our Laplacian operator, right? T plus Q met equals 0. And we actually do have a Q met this time. Let's actually take a look, right? When we write this out, remember we have a K, which we divide the entire thing by K and move it over to the Q met. Let's recall that, right? So we have R, d dr, R times dt dr plus Q met over K muscle, right? We're working in the muscle. So everything is muscle right now, right? Everything is muscle. This is the K that we get from actually multiplying or dividing it out, right? Km, there's a Km here. And it cancels out, right? This is the short form, okay? So now, what do we do? Well, let's move over the R. Let's keep it at d dr. R dt dr equals negative Q met over Km times R, right? We can actually, move the dr here. And then we take the integral, right? We did this before. This should be pretty redundant now. We have the integral of a derivative. We did this earlier. We have R dt dr is equal to what? Well, we have negative Q met, right, over Km, it's constant, times R squared over 2 plus C1, right? Plus C1. Now, here's where we can go in two different ways, okay? We have our expression, and now here's where we can go two different ways, okay? And let's say you did it one way, try it another way, okay? Option 1. And these, I'm going to tell you right now, these options both work, which show you there are many ways to solve this problem, right? There's many ways, but this is just one of them. We can use the boundary condition that we just determined, okay? Boundary condition we just determined, we know the dt dr at a specific place, right? Remember, we said the C1 is a slope boundary, right? It's a slope boundary. Because when we move the R over, right? That's when you'll see its slope, right? We talked about this. It's the slope. So boundary condition number 5 gives us a slope at R equals Rm, right? And we know, right, that this slope is negative Q met over K RM squared minus RB squared over 2RM. We know this boundary condition, and we can plug it in into this expression that we have right over here. And then we will actually find C1, okay? Dot, 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 dot. C1 equals boom, okay? You're going to get something, okay? Or option 2, you can use boundary condition number 3, okay? Let's scroll up, look at boundary condition number 3. We said it's this, right? It's the interface boundary condition, right? And we know by this interface boundary condition, right? We know by this interface boundary condition that, well, if the K's are different, right? If the K's are different, the only thing that can be the same is for the slopes to be equal, which is 0, right? The slope at this interface equals 0, right? It also makes sense because the DTDR of the bone is 0 anyways, right? So if it's 0, it can't suddenly change at this interface. It's going to be 0 at the interface. So that means we also have another boundary condition that we could use. DTDR, R equals RB equals 0. Well, you tell me which one looks easier, right? Of course, option 2 is going to be easier, right? But if you're really trying to understand this class and you really want to see how this all works out, I recommend you try both. It won't take too long. Of course, option 1 will have a little bit more math, but it's a great way to challenge yourself and you know what you should get. You know the answer you should get. So ultimately, the C1 should be equal to each other, okay? They should give you the same C1, okay? So we're going to say C1 is star, okay? From this point on, C1 is star. So go ahead and find C1, okay? So after you find C1, we're going to keep going, okay? So this is 2 ways you can find C1. Now, again, running out of pages, we have R times DTDR. I'm just rewriting what we had above. It's negative Q met 2km times R squared plus star, okay? Plus star. Different color star, that's okay. So that means we're going to move the R over on the other side, right? So we have DTDR equals negative Q met over 2km times what? Times R, right? Because we divided by R. Plus what? Plus star over R, right? That means when we take the integral of both sides and move the dr over here, right? That means we are going to get what? Well, it's the integral with derivative once again. So we have the temperature profile. Yay, we got it. The temperature profile is negative Q met over 2km times R squared over 2 plus star natural log R. See, again, all things we've done, plus C2, yet another constant, right? Now, use another boundary, use boundary condition, we know. What do we know? Well, this is boundary condition number 4, right? We know that the T at R muscle, right, is Tm is 30 degrees Celsius, okay? We know this. So I like to usually keep it in the Tm form just because I know that if I'm writing numbers and rewriting them again, I prefer to just plug my numbers in at the end, okay? So we have Tm equals what? Q met 2km times Rm, right? Rm squared over 2 plus, we have star, we have natural log, we have Rm plus C2, right? And we can then solve for C2. Okay, solve for C2. Then once you solve for C2, then you can solve for TR. Okay. Great job. Once you get to here, you just solve the boundary value problem. Good job, right? And the question asks, what is the temperature of the bone, right? What is the bone temperature? Well, all you have to do is plug in the RB, right? At the bone, right? And also one last thing to note is in Roselli-Diller, we have the K values as indicated by K times 10 to the 2, okay? 10 to the 2, which means you need to account for this 10 to the 2 and bring it back, right? So that means move that decimal point, right? So make sure you account for 10 to the 2 in Roselli, okay? You need to change it back to the normal K. Okay, so that's the end for part 1A. Let's talk about 1B. So it says, if the muscle tissue layer is surrounded by fatty tissue 1 centimeter thick, so we have, okay, great. So now we have another layer. Maybe I'll draw it to scale. That's not to scale, I apologize. Okay. So if we're drawing this to, so we have 0 again, right? 0 centimeters. Then we have RB, right? Actually, we'll just do RB equals 2 centimeters. Then we have our M equals 5 centimeters. And then we have this new RF, right? Equals 6 centimeters. RF is the fatty tissue, fat, okay? So we have this thickness as 1. And it's asking us, what temperature could the outermost surface fall while keeping the bone at the original temperature? So it's asking us, if we keep the bone at the initial temperature, don't be confused by the wording. We know by the previous question right here at this interface, this red interface is 30 degrees Celsius, right? And then we know the bone temperature from there. We know, right? We know the bone temperature. So if we change this, right, we're going to change the bone temperature. So we can just work with this being known, okay? We know that the T temperature of the muscle is 30 degrees. That's an indicator of the temperature of the bone, okay? So think about it that way as well. So it's asking us to set up the revised boundary value problem, including a figure as usual. So here, what you can do is you can list all your known boundary conditions here, right? To set up the boundary value problem, right? So list up your boundary conditions here. Again, very similar as above. Once again, same as above, okay? And again, right? Same as above. I've written this out 3 times now, okay? Or more. So set it up, right? We don't have QMent, right? And in terms of setting up, this is fine, okay? So write down those boundary conditions and then get to this point, okay? So now, what is part B asking? It's saying now you can use equations 8.6 and 8.7. Well, you only need 8.6, okay? And 8.6 is 8.6, sorry, I have some pictures now. Okay, so 8.6 is this equation, and it essentially is saying this is an equation to modify your question to include an annulus, annulus, I'm not sure. Okay, and that means we have this, right? So it's a modification for this kind of shape, okay? Like this, okay? And isn't that great? This is literally our fatty tissue layer. We're adding this to make our lives easier. This is Roselli 8.6, okay? So this means, right? So the Q leaving, right, the muscle layer is going to equal the Q of this fat layer, okay? That's our assumption that we're making, okay? So that means our Q of our fat layer is going to be equal to Q of our muscle layer, the in, right? At this interface, at this specific interface, okay? At this interface. So what does that mean? Let's write it out, okay? So we have, as we wrote earlier, what is the Q that we did? Well, we said it's Q met, right? Metabolism of, right? Our volume, right? Our pi, Rm minus Rb times L, right? We said this. We know this, okay? We know this. This is from our, right? Our muscle layer. Okay, so essentially, we're going to be plugging this expression in right over here. So we have 2 pi L K, which is for the fat, Kf, and then we have temperature in and temperature out. And that means we have right over here, we have the temperature in being the temperature of the muscle layer at 30 Celsius, 30 degrees Celsius. We already know that. And then we also have the temperature out, which is the fat layer, which is at radius F, which is 6 centimeters, right? That's 5 plus 1, a thickness of 1. So that means we're going to write right over here, we're going to write Tm minus Tf. And that's going to be over natural log of the radius out, which is the radius F. So keep this in mind, it's really easy to mess up here. Radius F over radius muscle. So we have this expression right over here. So what can we cancel out right away? Well, it looks like I can see a pi expression. Oh, and let me show write this right here. This is our fat layer. Okay. So it looks like we have pi's that we can cancel out. We have the length we can cancel out. And other than that, I don't see really anything else we can cancel out. So what we're going to do is what? We need to find the temperature of which the outside drops to, or it's asking what is the outside temperature with this layer, right? That's the temperature that the outside can drop to, because we thought originally the outside temperature was 30 degrees. So actually the new temperature is the actual, it represents the potential drop, right? It represents the potential drop. And it means it can be this new temperature. So let's say we have a new layer, right? It can be this new temperature outside, and our bone will still stay the same, or our muscle layer will still stay the same at 30 degrees with this new temperature, okay? That's what it's saying. Okay, that's why it's great, right? Insulation, pretty cool. So what we're going to solve for is TF. All you need to do is rearrange everything and then solve for everything, okay? So I'll just actually rearrange this real quick. So we have, looks like TF, once you rearrange, so we can actually do Q met Rm squared minus Rb squared bone, right? Over, looks like we can move the 2Kf times natural log Rf over Rm, what? And then we have, this is actually minus Tf, and then we have minus Tm. And we can actually multiply this times -1, and we will have Tm becomes positive minus this value, which makes sense. So we have 30 degrees as our Tm, right? And then we have minus something. So we know our TF is going to be lower, right? So that's how we do know this to be true. And we're going to be just plugging and solving for all of this, okay? And then you should have your final answer. So that is the walkthrough for question 1. Let's jump right into question 2. All right, everyone, let's get started with homework question 2. This is about heat generation and removal in the brain. So let's get started. So the brain uses approximately 20% of the body's oxygen when a person is at rest. Blood to the brain is delivered and recovered by the carotid arteries and jugular veins, respectively. So it's delivered by carotid and recovered by jugular. Notice how I use the different colors, okay? Great. Heat generated by metabolism in the brain can be carried away by the venous blood or conducted through the skull and scalp, okay? So we have heat exchange to and from the brain occurring through blood perfusion, not through the surface of the head, okay? So any of that skin we're not really taking into consideration, okay? So we have average combined flow through the left and right common carotid arteries. So we can just say carotid artery flow is 700 mils per minute, okay? And we have the concentration of oxygen bound to hemoglobin in atrial blood is approximately 8 micromolar per mil, okay? 40% of the oxygen delivered to the brain by the carotid arteries is released and consumed in heat-generating metabolism. Oh, I see heat generating, right? There's our first word. It talks about generation. Great. And it takes 28 kilojoules per mole to release oxygen from hemoglobin. Great. Energy released by the metabolism of carbohydrates. Energy released. Okay, another one, right? Energy released, right? By the metabolism of carbohydrates is 470 kilojoules per mole of oxygen consumed. So also I see oxygen again. So that's also interesting to know. Per mole of oxygen. Then we also have per mole of oxygen here, right? So that's interesting. And then we have the heat capacity of blood at 3,700 joules over kilograms times Kelvin. Okay, so if it's asking if the blood in the carotid arteries has a temperature of 37 degrees, what will be the temperature of blood in the jugular veins? So what is this question really asking? Sure, it's asking about the temperature difference, right? We are actually always talking about what? The conservation of energy, right? Oh, it's, this is the principle, right? What drove our principles last quarter? It was conservation of mass and conservation of momentum. We ingrained those in our head, right? We're always talking about, well, what's the accumulation of energy, what's the in, out, and what's any surroundings or generated, right? We always talked about this. If we actually think about it, what this actually is talking about is there is heat metabolism, there is energy. Where is there energy in this? Well, it looks like we have heat generating metabolism, right? So we have metabolism, right? Our metabolism generates heat, right? So we know metabolism generates heat, okay? And it's asking, right? What is this metabolism? In metabolism? Well, metabolism is in 2 steps, as we can see above. It first occurs, right? In what? The blood, right? Blood delivers oxygen. And then what? We have oxygen release, right? we have energy required for O2 release, right? Then what else do we have? Then the O2 consumed, right? Then O2 consumed is also energy, right? It says it produces energy, requires, produces. Okay, and then we have the blood leaves, okay? Blood leaves. So we can see that metabolism has O2 release, so that hemoglobin, right, which is part of those blood cells, it releases that oxygen, right? It unbinds and it requires energy to do that. How much? 40%. 40% of this O2. So 40% of the O2 that's delivered by the blood is being released, right? So let's take a closer look at the question. We have, right, the kilojoules per mole O2, per mole O2, okay? We are given our something mole O2. So let's actually write it out. Heat metabolism occurs, right, when we have O2 release and we also have O2 consumption. Okay, so this one is, right, negative 28 kilojoules per mole O2, right? And then we have plus 470 kilojoules per mole O2. What do we always talk about in this class? How do we need to calculate the change in temperature? Well, it's about blood flow, it's about change, and we're also given our heat capacity, right? Heat capacity is a hint. Where do we use heat capacity? Let's work backwards. Well, we use heat capacity in our expression Q equals MC delta T, and looks like we have our answer right here. So we're going to work backwards. We know we need the change in temperature, and we know it starts at 37 degrees, right? We need to know this. So if we need to know this, that means we need to know what? We know CP. We don't know Q. We don't know M. So let's talk about Q. What is Q? Q is heat flow. And what is its units? Q, we know heat flow is in watts, or also, as we know, joules per second, right? So if it's in joules per second and we have a kilojoules per mole expression, we need to know what? Remember, that dot means it's a rate. So we need to know, right? If we actually look at the units, right? We have kilojoules per mole, O2, right? What do we need in this box to get joules or per second, right? We need some O2. We need some mole O2 per unit of time, right? We need some mole O2 per unit of time to get joules over time, right? To simplify things. So I want you to take a look above and see what are the essential parameters, right? To get that mole over time. We know, for example, we know the flow. We know the flow. We know mils per minute. So we know the flow, right? Flow is mils per minute, okay? And we also know the concentration of oxygen, right? Concentration, we know concentration, right? We know concentration is micromole, right? Per milliliter, right? And we also know 40% of it's consumed, right? 40% of the moles, right? 40%, right? So that's also 0.4, right? 0.4 out of 1, right? So that should give you enough information to keep going on this. And then, right, what is m dot? Well, another way to write m dot, right, is also a rho times volume, right? Rho times volume, right? That gives you mass, right? And what is volume, right? Well, the change in volume you can determine easily. That is your flow. You know your flow. You are given your flow above, okay? Your flow is, again, right here. You know it. You're given the flow. Okay? Right here. 700 mils per minute. So you have your flow. You also know the density of blood, or you can look it up online. So you have your M, right? And then you should be able to calculate delta T, and you know it starts at 37 degrees Celsius, okay? So you should be able to find that final temperature. So that's what you're really looking for, the final temperature. Great. And for part B and C, it's asking if the volume of the brain is 1400 mil, what is the volumetric heat generation rate Q met? Well, as we know, since we already have Q, big Q, we already have big Q. We know through Fourier's that it's Q met is going to be the big Q divided by the volume, right? The volume of the brain. So that should be a very simple calculation that you can do to get Q met, Q metabolic. And lastly, and also one thing to keep in mind is the units, right? Making sure we're converting milliliters to meters cubed very carefully. And lastly, for part C, it's asking if flow through the carotid arteries is decreased. Do you expect the temperature to increase, decrease, or stay the same? And my tip for this question is to think about what we just defined as the equation for our Q, right? Well, we said it's Q, delta Q is equal to M CP delta T, right? So we are solving for delta T, right? We want to see that change in temperature, right? So, oops. Oh. So that means it's going to be Q over M CP. And what I'm going to ask you to do is think about what each of these are, right? What we just determined. And we should know that both of these, both Q and M, both have some flow term that's a part of this expression. To see what those parameters are and see how delta T is going to be affected by a change in the actual flow component of these two terms, okay? And this will tell you the relationship it has on delta T, if there even is a relationship. So that is the end of question 2. If you do have any additional questions, I'm more than happy to help answer them via email. So please send me an email, more than happy to help. Good luck with finishing up this homework and have a great rest of your night. Thanks for watching. Take care.